Hello everyone. In this video, I'll be going over the Module 6 Master TA lecture for CIT 247. So lecture topics include an overview on routers. We'll also be discussing routing tables and sources of routes. And finally, we'll end with a discussion on traffic flow in multi-LAN networks. So let's go over some general facts on routers. A router is a layer 3 or network layer device that is used to forward IP packets from one LAN to another. Now, this is unlike switches, or at least single layer switches, which are confined to forwarding traffic between devices that are in the same LAN. A single layer switch cannot forward packets to devices in different LANs. In order to do that, you need routers or layer 3 switches. So like VLANs, routers break up networks into multiple broadcast domains or LANs. Again, this is unlike a switch without VLANs and a single layer switch, which is confined to which creates a single LAN or broadcast domain. Actually, multiple switches connected together can also create a single broadcast domain or LAN. Routers, however, break these divisions up. They break them up into multiple LANs or broadcast domains. And just as a review, these two terms here, broadcast domain LAN, they pretty much are synonymous, as I discussed in previous lectures. But anyway, another unique feature about routers is that, unlike switches, we apply an IP address to every used port on a router. So in other words, when you would apply an IP address to a switch, you pretty much just apply it to the virtual interface on it, like VLAN 1. Now that IP address pretty much is just to remote into that device, like through SSH, for example, for like configuring it with Telnet or through Telnet or SSH. However, with routers, we need to apply an IP address to every single port that we're using on a router because each port represents a broadcast domain or LAN. I'll show that in a minute. But anyway, also each port on a router creates a single broadcast domain, as I mentioned. And finally, and therefore, each port also needs to be in a different subnet. And this is a diagram from the professor's lecture slides, but I'll be using it here to demonstrate this. So, as you'll note, each router interface there's something unique about each router interface. For example, each one is in a different subnet. As you can see here, all these are /24 networks. Each of these ports on the router are part of a different subnet or a broadcast domain. So, for example, you have the FA00 interface here. It's connected to this LAN here. Notice that the IP address here is different from this one, or is in a different subnet than these two interfaces, which are also connected to their own LANs. Also interesting to note is that a LAN here, there are the two routers connected to one another. These two interfaces here, that is actually a broadcast domain in a LAN. It's something to keep in mind for later for later assignments and stuff. But anyway, yeah, so just remember that each used port on a router creates a different subnet or different broadcast domain, and therefore needs to be in a different subnet. So routing tables. So routers store many types of routes in what is called a routing table. As the name implies, this table provides a list of all routes used by the router. Now these routes are used to help routers determine where to send packets. So this image is taken from study-ctna.com. But anyway, if you type in, let's see, show IP route, you can see that you're given a bunch of codes that represent the types of routes that are listed. And then you see the listed routes. So this is a static route right here with the S. And then this is a connected route. We'll discuss these types in a moment, but notice how the routing table basically compiles all the routes that a router uses to determine where to send traffic. And you can access the routing table by typing show IP route. So, sources of routes. There are three major types of routes that a routing table can record. For example, there's connected routes. If you look back here, connected routes are represented by the C code or the C code here. But connected routes are created when two adjacent router interfaces have IP addresses configured on them and have the no shutdown command configured. So basically, these two IP addresses will be in the same subnet, and these two interfaces need to be active. These two steps are what is needed to create created route or connected routes. So basically, they're really simple. Right here, as you can see, it's just a subnet listed, and it says directly connected, and then the interface that's a part of the connection. So static routes, on the other hand, are created manually by the administrator. They're a bit more complicated to create, and I'll be discussing them in the next slide, but you notice here that S, the code S, represents a static route. So it goes by a subnet via, it shows the subnet that's the destination, and then it shows the IP address that leads to that subnet, which I'll discuss in a minute. But so then we have routing protocols. So that's something we'll be discussing later in this class, but these are created automatically. These routes are actually created automatically by the routers themselves, but you need to set up a routing protocol before that can occur. So we use OSPF in this class, but other routing protocols include RIP and egrep. Not used in this class, as I said, but OSPF is. So creating static routes, this is something you'll need to do for your lab assignment, so I'll be going over it here. So with the diagram above, let us say we want to create a route for router 1, we're configuring router 1, that can get to the 192.168.1.0/24 subnet on R2. So it's this subnet right here we're looking to get to. It's this subnet on F0/0. It's the subnet that's on the F0/0 interface on R2. So the following is the command you would use. You would use the IP route followed by the destination subnet ID, followed by that destination subnet mask, and then the IP address of the next hop port or the exit interface on the source router. So that's a lot to unpack. Let's go over each part. So obviously you type in IP route and then space. Then you configure the destination subnet ID. This is the subnet you want to route to. So in this diagram, it's 192.168.1.0, as we discussed in our scenario. So next is the subnet mask. That basically just corresponds to the destination subnet ID, which is just 255.255.255.0. Finally, the final argument can either be the IP address of the other router's adjacent interface, which would be 192.168.0.2, or the source router's exit interface for that route, which would be S0/0, because this is the port we would use because it leads to the router that can go get to that subnet, that can directly get to that subnet. So with this information in mind, we would then use one of the following commands for this scenario. You only need to use one, but we can either use this, or the first command, which uses the adjacent the IP address of the adjacent port on the other router, or the port name of the interface that leads to the router that can directly get to the subnet. So our final topic for today will be very important. It's the traffic flow in multi-LAN networks. Understanding how traffic flows between routers is critical to your success in this module's lab assignment, and is critical in general to understand. It's very important information. So this information can be found on pages 369 to 371 in Volume 1 of your textbook, but this lecture here, I'm going to demonstrate this process with the diagram below. So we have a computer connected to a switch, which connects to another router, and we have two router interfaces connected to one another, and finally the second router connects directly to the other PC. So my discussion assumes that ARP has already taken place. We're pretty much just discussing the ping process. ARP has already occurred. We're not focusing on ARP in this scenario. So the first step. So let's build our scenario. So PC1 wants to ping PC2. So the former computer, PC1, starts by checking if PC2's IP address is in its local subnet. It does this by using its own IP address and subnet to determine this. So basically, when two PCs want to communicate with each other, they basically check if the destination PC is in the source PC's subnet. So obviously it's not in this case. So when PC1 finds that PC2 is outside its LAN, it then creates an IP packet containing its IP address as the source address and PC2's address as the destination one. So notice here that PC1 is actually routing. It is working in layer 3 right now. PCs can actually route to one another with their IP addresses and subnets. They can perform calculations that basically determine whether or not a PC is in its is in its LAN. So basically, we'll see what happens when the PC is not, or the destination PC is not in the source one's LAN. So this packet that PC1 just created is then encapsulated in an Ethernet frame. This is important here. So you've already heard about this in other lectures, but basically packets are encapsulated into Ethernet frames. And basically that's how they go from one device to another. And that even includes routers, as we'll soon figure out, or we'll soon find out in this demonstration. But this packet from PC1 is then encapsulated in an Ethernet frame. This frame contains the computer's MAC address as the source address. The PC then uses its ARP table to find the MAC address of its default gateway, which is F1/0 on router 1, and then uses this as the frame's destination address. This frame is then forwarded to IOU1. So notice that the MAC address is not the destination MAC address is not PC2's. So when traffic flows from within a single broadcast domain and needs to go from LAN to LAN, the frame basically contains data within the devices that are in the same LAN. So PC1 can't use the MAC address for PC2 for the frame because IOU1 is not going to know it. However, IOU1 understands what the MAC address for R1 is, so therefore that's what PC1 uses. So PC1 has a default gateway. Basically, what a default gateway is an address that helps PC1 send frames to a device that can send those frames out to different networks, or packets to different networks. So after encapsulating this frame, PC1 then sends the frame to IOU1. So our second step here, notice how the ports here are circled. I circled, these are the ports that are involved in this next step, the next major step here. So IOU1 receives the Ethernet frame from PC1. The switch then examines the destination MAC address in the frame, compared it to the MAC address table, its MAC address table, and then determined that the address belonged to F1/0 on R1. The switch does not alter this frame. So in other words, it's simply forwarding it. So after examining the destination MAC address of the frame, it sends it to R1. So the frame stays the same from the switch. The switch is just doing its job, sending the frame from one device to another in the same LAN. And then this frame is received upon F1/0 on R1. So in our third major step here, R1 then receives the frame from IOU1. The router then decides whether it should process the frame through two steps, or two tests. The first test is whether the frame passes the FCS check by having no errors, and whether the frame's destination MAC address matches the one for its interface. So the destination MAC address was for F1/0, and the switch already figured out that it was. The router does that too. So once these tests pass, router 1 then decapsulates the frame to examine the IP packet. So basically, the Ethernet frame that got the packet from PC1 to R1 is destroyed. It's no longer needed. It's decapsulated. The router then compares the destination IP address in the packet to its routing table, determining that the frame needs to go to the 192.168.0.2.0/24 subnet. So matching the packet to the route corresponding to that subnet, R1 encapsulates the IP packet in a new Ethernet frame with the MAC address of R2's S0/0 interface as the destination address. This frame is then forwarded to R2. So notice in this step, routers still use layer 2 stuff. They still use IP packets or Ethernet frames. So even though routers are used to forward packets, these packets can't travel between devices unless that packet is in an Ethernet frame. I'm sorry. Yeah, an Ethernet frame. So every time a router forwards a packet, it goes into an Ethernet frame that contains the MAC address of the destination ports in the LAN. So anyway, our final major part here is that R2 then receives the frame from R1. It then decides whether it should process the frame using two tests. It's the same test as before, the SFFSC check, and then checking the frame's destination MAC address. So when these tests pass, R2 then decapsulates the frame to examine the IP packet. It does the same basic check that R1 did and determines that it needs to go to the subnet, or this subnet here, PC2. So then it matches the packet to the route corresponding to that subnet. It encapsulates the IP packet in a new Ethernet frame with the MAC address of PC2 as a destination address, and then the frame finally arrives at PC2. So that's basically how traffic goes, or that's basically how packets travel through a multi-LAN network. These steps here will all be very important for your lab assignment. Please keep them in mind as you're answering the questions. So anyway, that's about it. Thank you very much for watching this lecture. I hope you found it helpful, and I hope you have a good day. Thank you.